Hello, everyone. Today, I'm going to introduce our recent work, ConvBoost, boosting ConvNets for sensor-based activity recognition. This is a joint work between Warwick University, Newcastle University, Northumbria University, and Georgia Tech. I'm Yuguan from Warwick. The outline is the first, wearable-based HAR, human activity recognition, the background and the motivation of our approach. And I'm going to introduce a general idea of our approach, ConvBoost, and also I'm going to show some experimental results. So the pipeline, I believe everyone quite familiar with the pipeline. We got the data streams, we use sliding window, and we track features, and we perform classification to classify which activity it is. In early works, we use sliding window, we track features, handcrafted features, and then we use pattern recognition algorithms like random forest, support vector machine. And since 2015, researchers start to use deep neural networks, mainly convolutional neural networks. However, for deep learning-based approach, lack of annotation is a major problem. So recently, lots of works were proposed for additional training data. For example, self-supervised learning, which take advantage of the pseudo labels, or cross-modality IMU data generation. One of the most popular one, IMUTube. There are also use ChatGPT to generate skeleton to generate, IMU data as well. Very cool approaches. So our core question is, we know, to solve the problem, we need additional label data. But how to do it in a simple yet effective way, lightweight way. So we take one step back. We look at a sliding window, and we ask one question, very simple question. Can we get additional label training data at the sliding window approach? Because normally we just take sliding window for granted, but there are lots of things we can explore at the sliding window stage. Okay, sliding window, very straightforward. We got data streams, we use the sliding window with a certain percentage overlapping, like normally 50%, and we got the training frames. And we use that to train deep neural network. That's what we normally do. Okay, so the training frames are fixed, which may result in limited number of training frames. And here, we propose random framing. We call it R-frame. And we introduce one variable, data. It's like an epoch-wise variable, which means for training epochs, every time it's a random number. So for the data streaming, we chop data time step off. And then we apply sliding window. Then we got that. And we apply bootstrap, and we got a training frames. That's only for one epoch. So it's an epoch-wise process, so we're going to get lots of training examples compared with the traditional one on the left-hand side. Okay? That's how we create more training examples at the sliding window stage. And, because that's at the sampling stage, sliding window stage, we call, in our ConvBoost, we just name it as a sampling layer. And our frame is just an implementation. We call it booster because it can create lots of training examples. It can boost the performance. And of course, we additionally built another 2 layers, concept layer, high-level layers, which can generate data from a different perspective. We call it data augmentation layer and also resilient layer. Here comes question, booster 2, booster 3. The actual implementation. Actually, in booster 2, data augmentation layer, we just use some existing approach, mix up, which is based on 2 training frames. We just combine them and generate a new one. And third one, resilient layer, we just use channel drop. We just to simulate the reality, when there are data missing in certain channels, we just replace all the value to 0. So these are our 3-layer structure and those 3 boosters. And Well, we generate lots of data, and it's an epoch-wise process. And then we can apply those additional data on any ConvNets. And at each epoch, we generate a classifier, and now we need to aggregate them. The simplest way is, based on validation data, we choose the best and use that for testing. That's a traditional way. Another way is, based on validation data, we choose a subset to form an ensemble. With the ensemble, and we use that for classification. Those are the two modes in our framework. Next, we're going to go through the experiments. The first, we're going to test our framework on 3 ConvNets, CNN, ConvSTM, and attention model. And also, we're going to test our aggregation mode, and also followed by some possible extension, more boosters, ensemble compression. We're going to test our framework on 3 public data sets, Opportunity, PAMA2, and GOTV data set. And the evaluation metric is mean F1 score. So first, the backbone, the traditional approach. Very straightforward, traditional sliding window, ConvNet, classification. Those are the F1 score on those 3 data sets for CNN, ConvSTM, and attention model. Now, we apply our ConvBoost. Then we got lots of training examples. And you can see for the proposed ConvBoost single best, the performance gain is quite significant. It's like 6–7% performance improvement, which means, of course, we got additional training examples. Definitely, it's going to improve the performance. And also, when we apply the ensemble mode, it can also further improve the performance. But the performance gain compared with the single best, it's not that much. It's only like 1 or 2%. But still, you know, ensemble is the best. But, well, you know, like in our experiment, the ensemble size is 20, so which means it introduced lots of model parameters. Okay, and also we did some applications today. You know, like the experiment we showed in the previous slide, that was based on 3 boosters. And also here we show we could use any 2 boosters. We can still see the significant performance gain. Okay, here comes the question. Can we use additional boosters? Yeah, this is like a framework. You know, boosters actually we can define. We just do some like a simple experiment. In the data augmentation layer, instead of only use mix-up, we just use R frame to generate training example again, and the mix-up with the original R frame in the sampling layer, okay? And we got the performance gain. And the second experiment is we also additionally apply scaling operation in the resilient layer. And we can also see the performance gain. The performance gain is not very significant because we just try to test, well, our boost is extendable, yeah? But because it's quite flexible, more boosters can be added for further performance gain. For example, the advanced boosters like self-supervised learning, or like use YouTube to generate, you know, synthetic data, put that into our data augmentation layer, or use domain knowledge-driven booster, put that into resilient layer. Because, well, what I discussed here is human activity recognition, but basically it's any frame-wise, you know, time series classification. You know, imagine you do sleep stage classification, and well, you can also use the approach, but you know, instead of you know, dropping the channels, you could take the domain knowledge into account and design your own booster. The second extension is ensemble compression. We demonstrated it. Ensemble is better than single best, but performance gain is only a little bit. Well, 1% or 2% at the cost of a large parameter number. Now we want to compress it. There are lots of model compression approach, but our epoch-wise ensemble, well, that's a unique character. Because, you know, every epoch we generate a model. Over the epochs, the model parameters can be roughly deemed as a Gaussian distribution. So we just average them. We average them, which means we just use like a mean model to represent the ensemble. And here are the results. Well, on the x-axis, that's a parameter number. On the y-axis, that's a accurate mean effort score. You can see the blue one is the ensemble, very large. And because in ensemble, we use 20 classifiers, so if we just compress it, the parameter number, the orange one, gonna become 5% of the parameter with comparable performance. The blue, the green one is single best. You can see with ensemble and compression, we can get a small model with higher performance. So we're back to our question. How to generate additional label training data, ideally in a simple yet effective way. The answer is ConvBoost. Okay, and the ConvBoost is quite flexible. 3 concept layers. You can use our booster, or you can propose your own booster. And also there are 2 aggregation modes: single best and aggregation, and also ensemble. Ensemble, you can further compress it. And the backbones, it's, well, backbone friendly. Basically, you can use any ConvNets for that. The code is available, and thank you very much.
Thank you very much. Okay, let's take one question during, yeah, please.
Hi, thank you for your talk. I have one question regarding to the R-frame boosting layer. My first question is that the delta variable, is it randomly selected in a uniform distribution? Or, for example, normal distribution?
Oh, thank you. We randomly choose, so it's uniform distribution.
Okay, then my second question following is that if it's a uniform distribution, is it statistically same equivalent as, for example, multiplying the training data by length of the per data window, and by sliding each data in one time frame? Do you get what I mean?
Now, can you say again?
Okay, so for example, if you have a data set with a total length of 100 time frame, and you have the length of sliding window of 10, then my question is that if it's a delta is just uniform distribution, is it statistically equivalent to multiplying the data set? For example, it initially was 10 data sets.
I think I can answer it.
Yeah.
Oh, in our implementation, we use like a window size. We use half the window size, just a random number from 0 to half the window size, just a uniform distribution.
Then, so I think it is statistically equivalent to, for example, starting the sliding window from 0 to 10 and augmenting the data to, for example, to get 1 from 11, 2 from 12, and something like that. Sorry, I think we can.
This implementation detail can discuss later.
Okay.
Yeah, you're already asking more than 3 questions. Okay. Okay, let's move to the next.